Or mute. Hey, perfect. Here we are. So everybody can hear me clearly. Perfect. Thank you for the sound check. So hey, I'm Casey. Let's get that slide up there. I'm Casey. I am the director of product for Joyent, where our primary product is Triton. Triton is data center automation software, and Joyent is a software company. We are unique, I think, in offering the exact same software that powers our public cloud. We operate a public cloud, but we also make that exact same software available as open source to power private data centers worldwide. And so open source, container native for 10 years now, obviously not Docker containers all that time, but recently added Docker containers. And that is the extent of what I want to say about who Joyent is, because most of what I do here at Joyent is to figure out how people are using the technology, how people are using cloud technologies, cloud infrastructure to build modern applications. And of course, that leads us to DevOps, or if you will, the more recent term, because DevOps is sort of a dead term, SRE, Site Reliability Engineering. People are comfortable with that term. This is the right room to talk about SRE. Is that right? Not many hands. Has it already gone out of fashion? You're right. You're right. But it is nonetheless newer than DevOps, I think. Fair point. But nonetheless, either way, when it goes well, it looks like this. It looks like Bruce Lee playing ping pong with nunchucks. It is a thing of beauty. It is amazing, right? But Bruce Lee only trained, by the way, San Francisco's son, Bruce Lee, only trained 3 people. Now that's probably 3 more people than you'll get as qualified applicants for an SRE open position, but you know, and part of the problem is that it's hard to understand the training. It's kind of vague, right? It means to do the right thing at the right time, but how do you actually, what's the pattern? And when you press people on it, there is no pattern, right? There's a lot of wishy-washiness in how you can repeat this, and people have struggled to do this. And I say that not because I want to pick on GitHub, but if anybody can get this right, it should be them, right? And yet, we've suffered recently with a lot of downtime on GitHub. I love GitHub. I'm really sorry to pick on them about that, but truly, I think there are better ways to do this, and there are better ways to think about what we're doing here when we're building modern applications for distributed environments for the cloud. Now, what I wanted to do to figure out how to do this, of course, is look for inspiration in science fiction, where all the great things are foretold. This, I think, is the first picturing of a computer in a film. Now, it's the 1950s. In fact, it's 1956. So this is, of course, a nuclear-powered computer. It has almost 10,000 nuclear power plants powering it, and it's 20 miles on each side. It's a cube, underground, subterranean computer, 20 miles on each side. And because it's the 1950s, nuclear-powered, it's also electromechanical, not electronic, and they call it the Krell machine. It's giant. This nonetheless talks a lot about computing. It is self-maintaining. They talk about, in the dialogue, they talk about the fabric of the machine. This is 1956. Remember, this is a long time ago. But 20 years later, 1976, what we learn is that, of course, with weak physical security and the correct interface, you can, of course, steal the plans to the space station, save your friends, and then save the rebellion, and plot the rebellion. And so 20 years after the first use of computers, has had 40 years of special effects rework to make it look even better. But you know, this is computing. It also introduces this notion of serial hacking in computer movies, which is kind of interesting. This introduces the notion, I think, of ChatOps. I think this is from 1983, the first ChatOps interface that we've seen pictured. And of course, like all good sci-fi movies with technology, what we learn is that you can save the world, perhaps. Of course, you can also imperil the world with technology. But in this case, what we do is we play a game with a computer. Interesting stuff here. What I think we can learn here is, one, sci-fi computers are monoliths in a lot of ways, which probably persists some of the misunderstanding about network distributed computing and the fallibilities of the network. But and while physical security is obviously critical, especially on space stations, what are we learning here? There's, I think, some limits about what we're learning here, because for all of the sci-fi interest here, what we're actually doing is just using the computer for the most part, and it might as well be You've Got Mail, which obviously is not going to teach us anything about DevOps practice. But at least everybody is equally skilled with the computer in this movie. So what else can we do? Where else can we look? And I think it took us some time to understand the role of software and operations and software development in sci-fi, but this particular film, I think, introduces some things. First of all, it is infrastructure portability of our applications. Again, we're saving the world, don't doubt it. Infrastructure portability, and obviously self-operating code. No schedulers here, interestingly enough. And then I have to go to the second worst Terminator movie to introduce the scalability of sci-fi software in operations. So again, the second worst Terminator movie. We can get into this later about which one is the worst. But here we see that software can in fact be designed to self-operate, be self-aware, scale easily and automatically across a distributed set of computers globally. And that's pretty impressive, all right? And we had to look to sci-fi to understand that clearly. But what are the characteristics of all this software? What have we learned from these movies? Sample size of 2, of course, all right? Well, we've learned that the software needs to be self-assembling, right? You can't have this giant external orchestrator controlling it. It has to be self-assembling it. It has to be self-aware to operate in this way. It has to be self-healing. And it has to be, of course, portable across multiple infrastructure and scheduler independent. And when you have all those things, you have sci-fi software, sci-fi DevOps. I think that's worth considering. And so, again, the differences between movie DevOps and actual DevOps practices, I think, of course, is that we don't have a giant external scheduler and we don't have SREs in these movies. Like, why don't we have SREs? Well, let's figure out that in a moment. But I did promise in the title slide that we're going to look at movies and other questionable sources about this. So, let's see, this is 1970, I think, Conway's Game of Life, and it gives us this other idea about how to build self-operating code. In this case, it's the Game of Life. It sets out a set of rules by which your code can replicate, right? And so code that meets certain conditions can replicate, and that's fantastic. It actually gives us a really interesting idea for how to build code in the cloud, because you don't want to have to manage all of this stuff as it gets ever more complex. You want to set out rules by which it can self-operate. This gives us a simulation system that allows us to look at that and play with that and experiment with it, which of course leads to the 1988 Morris worm. People know the Morris worm at all? Yes. I knew there was going to be at least some people who recognized that, especially because all of my movie references, I was hoping actually I should say, all my movie references were so old. So I needed somebody in the room who would recognize it. So the Morris worm, if you haven't read RFC 1135, it's worth reading for people who don't know what the Morris worm is. This was ostensibly a plan to map the internet that grew awry. And so this was self-replicating code moving throughout the internet, moving through vulnerable services on the internet, on hosts on the internet, and demonstrating how you can build code. And actually, I think it demonstrates how you can use cloud APIs, use cloud infrastructure through these APIs. Of course, the APIs are vulnerabilities in all these services. So maybe you might say that's not the way to do it. So what is the correct way to do it? All right? And so the traditional approach to all this is, of course, you start with a developer. The developer builds a site full of kittens, puts it on the internet, in the cloud, of course. You get a rush of users. Unfortunately, you fail under the weight of those users, so you get an SRE. You get more dramatic pictures of the cloud. You get even more users, and still things fail, right? So why do we keep failing? What's going on? Well, I think that's worth looking into. This particular tweet, I think, offers some advice about why we're struggling with this, right? So yeah, Docker on our laptops is easy, but Docker in production, they claim, is hard. All right, get that picture, and then I'll advance the slide. All righty. Let's look at this in a easier to read format, perhaps. All right. So these are the issues named on that slide or in that tweet about what it is. And I want to actually force us to look at it this way. This isn't about Docker in production. This is about modern applications. Right? And if we're not answering these questions about modern applications, what are we doing how are we building our software, right? We could be having these same conversations, whether we're trying to build or rebuild everything as a microservice, or hell, let's refactor everything in Haskell. We have to solve all of these same questions. And I think they fall into, and we heard it in the earlier talk, these fall into the category of orchestration. When you build things at cloud scale, you exceed our ability to manage these things with human touch. We want to have better availability than you can get by putting people on a pager. We want to have faster response times in these things. We want to be able to scale faster, all of this stuff. So when we talk about orchestration, how many people here feel confident in what orchestration is? Give me, if I say orchestration, we say, yes, of course, why is this guy talking about orchestration? Is that the answer? Nobody. Oh, there's one hand. All right, like two, perfect. So we don't all have a lot of confidence about what orchestration is. Is that the thing? Is that the answer I can take from this? All right. I felt this for a while, and I've been struggling with it because I feel as though we all use different definitions for what orchestration is, and we all approach it from different ways, trying to get there. Well, let me just say it simply. Orchestration is not magic. It may be the things that we don't yet know how to do, but it is definitely not magic, right? We will figure it out. And for the most part, all we need to remember is that orchestration is just automated operations. Think about the operations that we need to do with our application and think about how to automate them, and that is orchestration. We can get it. And inevitably, it is code. And we're all people who are comfortable with code. We know how to do this. We can do this, right? So let's think about this in practice. Put it in context for a bit, because this is definitely worth digging into a little bit. This is our app. Very, very few apps, however, actually run on their own. In fact, very few of them are even as simple as this tiered application, right? With a web front end, main application code, and then some persistence underneath it. Of course, but even if you have an app this simple, it's probably going to be scaled if it's actually useful, right? And then the orchestration comes in, because somehow, one way or another, we have to figure out how to, first of all, how are we virtualizing the network? If it's a containerized environment, that's a new question. We didn't worry about this before containers. We assumed there would be a network to the instance. It's funny that we didn't assume that when containers came along, but how do we virtualize the network to that instance? How do we connect those instances at the web front end? How do we connect those to our DNS so that they're globally discoverable by everybody? Well, we can go in there, update the DNS by hand, and that's orchestration. It's human orchestration, but it's orchestration, or we can automate that. This especially gets interesting as we try to scale. For instance, our database, in this example, we try to scale. Suddenly we have to update all of the main application instances to know that there's a new database in place, right? So we have to update all of those. We can do that by hand, or we can automate that. And sometimes we have unexpected negative scaling events, and that means we have to update all of the web front ends to know that this particular instance is no longer available. Please don't send any requests to it. We have to do this stuff for every portion of our application. We have to automate those relationships, that configuration. This is discovery, service discovery and configuration, right? And it depends on a service catalog and then a process of discovery from that catalog. But for the most part, we usually build this external orchestrator. And we've been working at this problem in a lot of different ways for a lot of years now. For some people, this is Jenkins and Capistrano. For other people, it's configuration management solutions. We're in a container conference now. I bet you there's the room full of people, well, a large portion of this room assumes that we're going to do this with Kubernetes or Mesos or some very, very sophisticated Mesos framework. That is all fair, because that is the tradition for what we're doing. Keep in mind that all of that is effectively part of our application. It's another aspect of our application and how it works, right? So let's figure out how this plays out. We have our developer who's building on his laptop without the orchestrator, just building with these components, because the orchestrator rarely works on the laptop environment. But nonetheless, our developer can build that way. We have our SRE, who is responsible for making sure everything works, maintaining the application manifest for the orchestrator, and of course, figuring out how to scale everything. And yet, still, we're getting these errors. We're getting downtime. And why is that? Well, of course, we've got our developer working on his laptop and saying, works on my machine. We've got our SRE working in her environment, testing everything, maintaining the orchestrator, all of that stuff, and wanting to yell back at the developer, fine, give me your laptop, we'll put that in production. But our SRE is a little bit more restrained, and she's really qualified. So she looks at the problem and says, how can we do this? What can we do here? And what I think we get is orchestration out of control. And still, it leads to errors, right? Because the developer, of course, is working on his laptop without the orchestrator saying, it works on my machine. The SRE is working in her environment, testing, seeing that everything works, figuring out how to scale it. And maybe we'll eventually lose her cool. So there's a pattern in this. Did we see this? I think we can do better. I think we definitely can do better. And the problem is, I think, that the orchestrator too often is the center of our production world. Now, our app is probably the most important thing in our production world, but yet the orchestrator becomes the center of it. And that is like a pre-Copernican view of the solar system. This is a shame that it ends up at the center of the world, and it's still most often not running on developer laptops. So how can we solve this problem, this misunderstanding of the relationship between the orchestration and the application? Well, first of all, keep in mind that there are no big orchestrators in the movies. We are violating sci-fi fact, of course, when we add the big orchestrator. That doesn't exist, right? But more practically in this moment, keep in mind that your application, all right, its reliability is dependent on both the orchestrator and the app. That means it's dependent on both the SRE and the developer, but they're probably not working together. What do I mean here? Well, so because our developers are typically not running the orchestration in the laptop, because these things, when they're external orchestrators, they're big, they're complex, they're painful, they slow down development, there's probably not one developer in here who's actually doing application development rather than doing development of the orchestrator who is running that orchestrator on his or her laptop, right? And part of the problem here is that because of the way these things are built and separated, and because we're still struggling with how to separate secrets from code, even at the orchestrator level. So we pulled secrets out of our code and put it into the orchestrator, which is kind of sad. So because of this, oftentimes our developers don't even have access to the repos in which the application-specific orchestrator code exists. So they have no idea what's going on to their app when it goes from their laptop into production. You can't hire enough SREs to solve this problem, all right? Now, the frustration, of course, for the SRE is that all of the automation code built for an application and one orchestrator is specific to that environment. You can't move that to other orchestration environments. You can't learn, all you can do is learn in the abstract when you look at how it's implemented in other environments. You can't actually just copy and steal from other environments, which we're programmers, that's what we do, right? So that's what open source is all about. And the tight integration of all of these components, the orchestrator, the application, and the code that brings those things together, that makes it very, very difficult to move quickly. All of this push for containers is oftentimes about developer productivity, developer velocity, but the environments that we're using to bring these things into production are actually adding friction to erase all of the benefits, or erase many, if not all of the benefits of containers in the first place. And that, of course, leads to more frustration for our users, and it reminds us that the only reason probably that we're still successfully in production ever is because we have some really qualified people who make this look good, make running websites at scale look like playing ping pong with nunchucks. So what can we do? How can we fix this? How can we move past that problem? And the first thing I want to argue for is that we have to end that separation. We have to end that separation of our applications from what we do in development and what we do in production, right? We have to make the orchestration laptop friendly, right? In order to do that, we're going to have, because it's hard to get everybody to agree on a single orchestrator, and it's hard to get everybody to run the orchestrator everywhere, we have to make that orchestration portable and laptop friendly, obviously, so it has to work with very, very lightweight environments. And we have to keep that orchestration code with the application. It has to be available to the developers so they can see it, they can make changes to it when needed because they're making changes to their application. So making that everything portable and scheduler independent, right? We need to consider the relationship of our application to the scheduler and to the infrastructure and make sure we have clear boundaries between those layers. When we mix these layers, we add complexity, and we're still struggling with that. So I have some ideas about this. I took on a challenge a while ago to see if we could Dockerize Couchbase and automate it. Part of this was honestly just for a demo. And it went pretty well. What happened was that we were able to set it up so, and Couchbase is beautiful, it has a nice web GUI, that's pretty cool. And what we were able to do is set it up so that we could start it easily with nothing but Docker Compose, get everything running, have an application. In fact, it did everything that we expected in terms of being an environment where we could do all of this orchestration with a full application, be able to scale everything, including the persistence layer. And there's a whole app blueprint that we have on this. So this all works with no external orchestrator. But people ask, can I do this with a complicated application? How is this going to work with something more complicated than Node.js and Nginx and Couchbase? Of course, Couchbase as a persistence layer is pretty easy because it's built for clustering. It has automatic clustering in there. A lot of things work just automatically. Can I do this with something a little bit older, something not as easy to work with? So the challenge was, could I do this with a persistence layer that it has some legacy behind it, shall we say? Can I make MySQL demonstrate all of the features that we did with Couchbase? All right, of course, now what this means is, and forgive me for reading the slide, but it's kind of important. All right, can we make it like one button easy to deploy MySQL? Can we make it cluster automatically? We know that one of the frustrations about this is that it's a pain to cluster. We've got to automate backups. We've got to automate the bootstrapping of all the replicas, right? So that when we scale, we do a Docker Compose scale MySQL equals whatever, and you get that number of instances with one primary and multiple replicas, all automatically clustered, all of the replicas automatically bootstrapped, all right? And then if that primary fails, we've got to automatically promote one of the replicas and find the right replica to do this, promote one of those to the primary. So again, just to simplify it, we want one button deploys, easy scaling, and, not stated earlier, infrastructure independence, right? And so what we did was we actually took, we started with Percona Server, a MySQL compatible environment, and totally automated it. We're pretty proud of ourselves, so we showed it to Peter Zaitsev, founder and CEO of Percona, and asked him, what do you think? And he had these kind words to say about it. Basically, what he identified is that we have built database as a service simplicity into a self-running Docker image, so that you can do this without the lock-in of being in database as a service and without those costs, but still enjoy all the simplicity. What do I mean by that? Well, if you compare side by side the RDS versus MySQL, all right, our implementation of MySQL, we get feature parity with this, right? We get that ease of use, but it's still something that you run on your own. And if we compare a little bit deeper in the feature set, what we realize is that we don't have that lock-in that has made it very, very difficult to use RDS over the long term. And of course, we've also eliminated a lot of the costs because you're not paying for RDS, you're just paying for the infrastructure. And you can run it on your own infrastructure, bring it into your private data center, run it on your own. You can run it on your laptop the exact same way, right? When I talked earlier about developers running stuff on their laptop, one of the things that I didn't point out is oftentimes when you're dependent on these managed services, you can't even run with those managed services on your laptop, and you have to have some sort of feint on your laptop to be able to make it work, and that's another reason for those problems. So we needed a name for this. Once we got to this point, and we've been building applications, a lot of examples like this for a while now, what we didn't have until relatively recently is a name for the pattern that we're building. And as we looked at what we were doing and tried to define it very, very specifically, what we realized is that the autopilot pattern is what we're looking for, right? And the reason for this is that the autopilot doesn't replace the pilot. What it does is it aids the pilot. The pilot is still in control, but it automates the repetitive and boring tasks. In fact, let me give you a more specific definition, right? It automates in code the repetitive and boring operational tasks of an application, including startup, shutdown, et cetera, all of the operations, for reliability, ease of use, and improved productivity. This is also an incredibly self-documented pattern because everything is in the same repo with the application. So where does it work? How can we use this? Well, it works here. In fact, you could say it works everywhere. Pick your infrastructure, pick your scheduler, it works there because of the way it interacts with that environment. It works scheduler independent, infrastructure independent because of its approach by keeping the orchestration in the application rather than putting it out into an external scheduler. Now, we built a lot of different applications according to this pattern as we explored it. And so check out github.com/autopilot pattern, take a look at it. And some of these things we've documented on the Joyent blog. Come visit us, take a look at that. And I should say, all of this, what we've learned along the way is that there is some shared code that can make this easier. Nobody wants to rewrite their applications or add a lot of custom code to implement these behaviors inside their applications. So along the way, we developed Container Pilot. We used to call this Container Buddy, but in reference to the pattern, it makes easier sense to call it Container Pilot. This is open source, and to be clear, what it does is it helps our applications become infrastructure independent, support one-touch deploys, and easy, very, very easy scaling. Now, I said this is open source. It was just late last night that we had our latest pull request, adding a feature to support scheduled tasks inside the container by Justin Walker of Jet, totally independent or open source, and great addition for features. The benefits of this, I think, are pretty clear, but most importantly, let's build stuff. Thank you.